Okay, so we're going to do some part of this PowerPoint, the collisions and the laws that govern them. We won't do the conservation of momentum part, but we're going to do the momentum and impulse portion of it, and you're going to have to work the problems for it. And then we'll do the conservation of momentum part later in class. So in physics, there's a whole set of laws that govern how collisions have to happen. And collisions can be anything from the really big explosive things you might think of to just simple things like bumping into each other in the hallway. Those are all fall into the category of collisions, and there's a set of laws that these types of collisions have to follow. So we can define a collision as any time two or more objects come in contact with each other, causing a change in motion between either one of the objects. And we also include in that any internal explosion. That's going to be considered a collision also. So like a bomb blowing up or any of those sorts of things, that would also fall into the category of collisions. So the law that governs collisions says that the momentum of the system undergoing the collision is conserved. So that's the first law that all collisions have to follow. So there's a lot of this that we haven't really learned about, this idea of momentum, and then we haven't talked much about conservation. So first of all, let's define some bits and pieces of this. First, the idea of system. System is whatever objects are involved in the collision. So if you're walking down a hallway and you bump into somebody, it's you and that other person. If it's a pool table, it's all the balls on top of the billiard table. It's whatever you define as your system is what's going to be, whatever's part of the object's being collided, that's what your system's going to be. Conserved means remains constant. So it doesn't mean that all the pieces never change their momentum. It just means that all together, when you add it up, it's always the same number. So if you add up all the momentum before they collide and all the momentum after they collide, it's going to be the same thing. So now we have to talk about what is momentum, because that's the thing that is conserved. So momentum is whenever you take a mass and put it into motion, we say that that object has momentum. And it's a property that every object has. It depends on its mass, and it also depends on how fast it's moving, its velocity. So objects that are really massive, excuse me, that are moving very fast, or objects that are moving very fast, we would say they have a lot of momentum. So things that are small, that are slow moving, those are not going to have very much momentum at all. And the symbol we use for it is the letter P. It is a vector, so we will put the vector symbol over the top of that. Even though I can't do that on the PowerPoint, I will write it now. So this is a vector, this P. And it comes from the formula for mass. This is mass times velocity. So mass times velocity is what you use to find your momentum. So what we're saying is that momentum is conserved, which means that if you take the mass and the velocity of all of the objects in the system and you add it up ahead of time, and then their collision happens and you add up their masses and velocities afterwards, you're going to find that the sum, the totals, are the same before and after. That's the law that governs how collisions have to happen. And the unit for momentum is a kilogram times a meter per second. That comes from a mass times a velocity. Kilogram, meter per second. So here's some examples that go with momentum. I'm not going to work them here, but I do want you to work them, and we can go over them in class. They're very, very simple. They give you the mass, they give you the velocity. They ask you to calculate the momentum of the various objects, so it's pretty straightforward examples, but they're just using that formula P equals M times V. So you're going to go ahead and do those and then continue with the video. Alright, now that you've worked those problems, collisions and momentum. Collisions are what cause an object to change its momentum. So if you're moving down the hallway and you're minding your own business and somebody bumps into you, it's going to cause you to either not usually change your mass, but usually change your velocity. Some way you're going to slow down or speed up, or you're going to change your direction. So that's because you had a collision, and it's because the person placed a force on you. And that's really what's going on during collisions, is that forces are placed between the objects, and that causes the objects to change their motion. So if you're going to change your momentum, you're either going to change your mass or you're going to change your velocity. For the most part, we're going to deal with objects that are changing their velocity, but not necessarily objects that are losing or gaining mass. It can happen, but it doesn't have to. So when we deal with collisions, we're going to be talking about changing mostly the velocity of the object. So that brings me to this topic of impulse. And impulse can be a little bit confusing with the way that it is defined and what exactly it is. But basically, it's a change in momentum. Anytime you change your momentum, we call that you've received an impulse, or we don't really say you've undergone. We say you've received an impulse. So if somebody bumps into you in the hallway, we say that you've received an impulse from that person because you changed your momentum. And the amount that you change your momentum is equal to the impulse. So the momentum, your change in momentum is your impulse. You could also find the impulse by calculating how much force was placed and how much time that force was placed. So there's a lot of ways that you can calculate it. So this part is the change in momentum part. And then this is your force, what force is placed on you, and how much time it gets placed for. So if somebody bumps into you and it's very quick, then you're not going to change your momentum, versus if somebody shoves you for a far distance or for a long amount of time, you're going to have a lot more change in momentum, depending on how much force is placed on you and how much time it takes. And of course, your change in momentum can be found by finding the change in anything, which is the final minus the initial. So that's your change in momentum, final minus initial. Again, these are all of these that are bold printed, those are all vectors. So make sure you put the vector symbol over the top of those. Anything bold printed is a vector. Okay. So there's some real world applications of impulse. And since you will, I'm going to put this actual PowerPoint up on the Moodle site. I'm sorry. So you can go and check this link out on the actual PowerPoint. You just open it up and click on the link. It's just a video of airbags, but airbags are an example of impulse and how they help reduce the amount of force on you, because what an airbag does is it increases the time of the collision. Versus if you don't hit an airbag, if you run into something and your body just slams into the steering wheel or slams into the windshield, that collision happens very quickly. But if you have an airbag, it increases the time of the collision. And so what you end up getting is a change in momentum, where the time portion goes up, and as a result, the force on you gets to go down, since the change in momentum is going to happen whether or not there's an airbag or not. So this change in momentum portion doesn't change. This stays the same. But by having an airbag, you get an increased amount of time, so this number goes up, so the force number can go down. And that's how you're able to be saved in a situation, versus if you hit a windshield, the collision happens so quickly that in that case the time number is so low that the force number ends up having to go up to compensate. And so you get a lot more force on your body, and it's very, you get a lot more injury. The same thing is true with riding the punch. When you ride the punch, what that means is that when somebody punches you, you move with their body, you move with their hand, so that you increase the amount of time that their hand is in contact with your face. And you might think, well, that's weird, I don't want to increase the amount of time that somebody punches me, but actually you do want to increase the time, because by increasing the time, you get to decrease the amount of force that that punch has on your face. So that's why you end up riding with the punch, versus just standing still and allowing them to punch you very quickly. You actually get a lot more force applied to your body if they're allowed to contact your face for a very short amount of time. Similar situations have to do with like following through in baseball. So follow through means that you allow the bat to swing all the way around when you swing the bat, so that it stays in contact with the ball a lot longer. And this is a little bit different, because this time you're increasing the time that the two are in contact, but your force this time is staying the same. The amount of force that you swing with pretty much doesn't change. So what ends up happening, if you increase the amount of time that they're in contact, but you apply the same amount of force, you're going to see a very big increase in momentum change. So that means that the ball is going to end up going much farther. It's going to end up with a higher MV. And since the M doesn't change, it'll end up with a higher V. So that makes the ball go farther. So following through in baseball is important. You want to keep the ball in contact with the bat as much as possible so that you can make the ball go farther by giving it a higher final velocity. The last one is another example. When you go rock climbing, you should use ropes that have stretch to them. And that's for the same reasons as previous problems. If you have a stretchy rope, then if you have to fall, then the amount of time that you fall, that the actual stopping happens, it gets increased because you use a stretchy rope. And so therefore the force on your body gets decreased and you have less likely to get injured. If you don't use a stretchy rope, then when you fall down, if you happen to fall, then the rope stops you very quickly. And so that's a very short amount of time, and the force that's on your body is very large, and it can actually be damaging. It can cause you to break your back. So you always want to use a stretchy rope whenever you're rock climbing. There's a couple of other examples. I want you to watch this clip also, which is crumple zones in a car. When you have a car that is designed, this is the way cars are designed nowadays, is that they crumple up when something hits them. And that's actually important because that increases the amount of time of the collision. So you might think, well, it's a pain because now your car is totaled, but it's more safe for the people inside since the collision happens over a longer amount of time when the car crumples up versus if the car didn't crumple and it just hit into something and bounced right off of it. That's actually really dangerous for the people inside if the car doesn't crumple a little bit because the collision happens so quickly that the people inside get a lot of force on them. Okay? All right, here's some impulse problems for you to work. The formulas, again, for impulse are the change in momentum, final minus initial, which is mv final minus mv initial. And then also impulse, I should have a capital on it, there you go, can be force times time. And then you can actually set these two equal to each other. You can do one big formula, force times time equals mv final minus mv initial. That's one big formula called the impulse momentum theorem. Kind of sets them all equal to each other. And that's a good one to use. So when you read the problems, like you have to look, here's a mass, there's 15 meters per second is an initial velocity, it's being thrown. He catches it and brings it to rest, so there's your V final, and then there's a time, and they want to know the force. So you can use this big formula right here to figure all of that out, to plug in and solve for that. And here's another similar situation where they give you information. Just make sure that you keep in mind that one of these velocities is to the north, and the other is in the opposite direction, so that would be to the south. So you need to make that one negative when you plug it in. And then here's two more problems. I'm going to ask you to work all these problems. We'll go over them in class. And then we're going to stop there, and we'll finish conservation of momentum in class also.